Okay, so we will have one experiment or mini project for PLL, and today we will start DLL. So I will explain both of them, and I have one question. Do you remember in charge pump based PLL, I told you like what is the DC characteristic of charge pump plus filter last section, and then how you can derive it. I was talking about locking range, right? So because I assume that, for example, we have a phase detector and it has, okay, so say constant value multiplied by input phase will be the output voltage of phase detector. Now this constant will be that in fact conversion gain of phase detector, and of course for charge pump or for other types of phase detector, so and including charge pump, we can say that, okay, what is the output current? So output current is average current, which is given from charge pump to the loop filter, will be proportional to delta phi, right? If you look at it in open loop, delta phi is input, difference between two phases of input signals. Then you will have an average current from output of charge pump. So this average current and this delta phi have a relation. So essentially I is equal to delta phi upon 2 pi. Output voltage, average current is equal to delta phi upon 2 pi into current of current source. Okay. So this is the average current you will get at the output. However, the question was, if this is the case, we want to obtain lock range, right? So if this is the case, and then you look at DC, so therefore that effectively DC value of this voltage will reach to a very high value, because this is an integrator, ideal integrator. Charge pump is an ideal integrator. So you have a constant DC current, or in fact not DC, constant average current, which is flowing into the capacitor, is charging it, so it will increase. So therefore, how we can get the lock range of this PLL? Essentially, when we have a charge pump based PLL, what is this conversion ratio, right? That was the question. So, did you follow it? Anybody follow? I told you last time also, this might be a quiz question. So I don't draw, very well. Well, just ideally. You consider you have a charge pump based PLL, okay? Everything is ideal. Just you put two ideal current sources, two switches, and use just a simple RC, okay? Just an RC at the output. So this is. Okay, so just you have an VCO with a constant value of, one of you can. So now we have this charge pump based PLL. What we want to derive is what will be the CTL, which is the output of filter, with respect to delta phi at steady state. Therefore, you consider you have a step change at the input. What will be the final VCTL? VCTL is the output of charge pump of the loop filter, which was the input control voltage of VCO. This is A and B. So for that, you need to derive the transfer function, closed loop transfer function of PLL. I have already shown it to you. It's a simple second order, but do you remember I told you one coefficient of KVCO, you double check. That also was the one thing that I told you to derive and double check it. So then Now put it together, then we make it here. So you derive the transfer function, show what is the transfer function, and then now if it is, what will be the VCTL upon delta F. So delta F is a step change at, again this is at steady state. This is change in input frequency. Say for example, it can be a step change. No, for charge pump, just consider you have this at the output of charge pump. Just one capacitor, 1 R. So it is lossless. So this is I out charge pump. So charge pump is just a simple RC low filter. And C, suppose if you have a locking time of delta T, okay? This is, assuming you have a locking time of delta T, what will be the average I out of charge pump for case B? So you don't need to write time-dependent equation and this thing. So just from transfer function you can, and simple equations you can derive. Don't spend time on writing time transient equations. You don't need it. So for question A and question B, you use transfer function only and then say what is the final value of VCT. Okay, just as a point, I don't give it now as a question D, but then afterwards you solve it. If you have locking time for charge pump based DLL, then from that it's very easy to derive the lock range. Okay, so this I'm not giving as a quiz. It may not come directly in your mind now, but afterwards you just work on it. Anyway, if you write VCTL, it will be a function of delta F. So if you write it VCTL upon delta F, then it's not a function of delta. You don't need to use transient analysis, right? Just use transfer function, get the steady state. Okay. Please collect. Okay, so it is expected. What will be answer to first question? 0. Good. What will be answer to the second one? Good. And third one? Yeah. So then why did it take so much time? Okay. So you tell me I will write. See, locking time is given. Exactly. Right? That's it. See, quiz always is not very lengthy. Sometimes, but it is just, see what was the motivation. This delta VCTL, of course, this will be 1 upon K VCO, delta T is given, so this you will get. See, the main point is, this charge pump, this circuit, at steady state is unstable, right? Because at 0 frequency, if you give a constant current, this output will be infinite. That is the reason actually delta phi becomes 0. Because an input of this circuit at the steady state is 0, therefore this will maintain some voltage. That is obvious, right? Now, if you want to calculate log range, then what will be the proportionality constant of this circuit at steady state? There is no proportionality constant. That was the question. See, what I mean from proportionality constant? You have a phase detector. Output of phase detector at a steady state is proportional to the input phase difference, right? But here at the steady state, if you call it frequency equal to 0, at frequency equal to 0, transfer function of this circuit is not stable, right? Because one pole actually is equal to 0. Therefore, we should look during transient when it is locking from one frequency to another frequency in the lock range. During that, what would be the average locking time that can be obtained from the closed loop characteristic of the loop, right? You have, for example, a second order with system with imaginary zeros. Therefore, if you look at output VCTL versus time, for example, it will be oscillatory and then it will settle. So, for example, you can consider one cycle of this as locking time. So, this is now your time. But as soon as you have time, then you look at the average of the current which is drawn from this charge pump. And that actually will give you an idea of this coefficient. So, this is as a hint, you continue, then you get that proportionality constant and then see what is the log range of charge pump phase. So, do it as a small assignment. Yes, that is correct, but that itself will be, that is the range of VCTL. Now we want to map it to range of frequencies. Whether it is same as range of VCO or not. You just check. You to write it. That's right. Then for that you need to look at closed loop because open loop is not stable. Right? So you look at closed loop transfer function, you look at closed loop response and see what is the effective locking time. For example, you can consider if it is underdamped, therefore it is oscillatory. So for example, 1 cycle of it, 2 cycle of it will be the locking time. We need to have a time reference. Because in contrast to, for example, other cases, this is not stable at this equal to 0. Okay, so now DLL. I have one more example for PLL at the end of this lecture. We will talk about it, but now first let's start DLL, then we'll come back to. So just I wanted to tell you there is a difference between steady state and average. For average, you need to have a time boundary, a time interval. But a steady state means S equal to 0. So you could just get it from transfer function also, A and B, just putting S equal to 0, that is low frequency, will give you the same results. Okay, now because we can use PLL to log to a particular frequency, it is not very difficult to get other things out of it. One of the applications is in digital systems is when we have a clock. We want to generate other phases of same clock. For example, this phase. So this is phase 1, this is phase 2. So one way of generating these different phases, which are very much used in digital applications, is, for example, suppose you put 2 PLLs, right? In such a way, a steady state phase error is not 0. Okay, so PLL has been designed, which will have some steady state phase. Therefore, it is type 1, right? So now, in this system, so you have 2 PLLs, so you can design the PLL in such a way that will give you this phase shift of, for example, pi upon 2. But there are 2 problems with this. First of all, you want to have a PLL with a phase error of pi upon 2, right? That phase error is too large. That means that your loop gain is not too large. Therefore, that PLL won't be a very good PLL. So you will have a lot of change in this error because now your loop gain is small. The second thing is that you have 2 PLLs. Now these 2 PLLs should be completely matched. So therefore it's better to use one PLL and add different delay components to generate different phases. Of course, now the question is how these delay components will match. Then there are ways to improve this matching. So the first circuit, that is called delay lock loop, is essentially the circuit which locks, actually it is based on PLL. It locks at a particular delay at a given frequency. Therefore, here we consider frequencies constant and then just it locks at different phases. And it is not very difficult because now you consider a type 2, for example, right? Or even type 1, actually for phase not to be 0, even type 1 is, no, type 1 will do, yeah. Now suppose you have a PLL with steady state error of 0 at steady state is 0, okay? What does it mean? Means that the phase shift between the input frequency and output and VCO frequency is 0. Now suppose if this VCO frequency is given to some delay components which generate some delay. Or what is delay? Essentially delay means phase shift, right? So if they generate some phase shifts, then after a number of stages at the input of PLL, total phase is 0. Therefore, the total phase will be divided by the number of elements. You will get n number of phases. So therefore, the circuit will be something like that. So same charge pump, for example. So phase detector and the loop filter all together. This was one component. We keep it as it is. We have an input frequency, therefore we keep it as it is. F in or omega in and some phase. So output now will be a control voltage which will be given to VCO. Therefore this will go to VCO. Now suppose if this VCO is not a single stage VCO, right? And first of all here now we are not looking at VCO. It is given to just, so because frequency is constant, okay? It is given from outside. So now I replace VCO with some question mark components. So this should be, I have to connect it here because now it is used as a control. Just consider two modules. Okay, so there is no connection here. And this is the output, okay. Which is coming back here. So what I want to do is, instead of controlling frequency, here I want to, in fact, instead of frequency synthesizer, look at it as a phase synthesizer. So I want to generate phases. Therefore, here I'm not interested in changing frequency. I want to have some modules that I apply this VCTL to them, and they will change phase for me. Therefore, here I apply same signal here as input. So this is same, right? So F in, F in. So here this component will give me same frequency F in, but now F in plus some delta phi. Okay, and again here I will have F in plus delta phi. Now this is second one, so it will be 2 delta phi, right? So at the input, I make it in such a way, for example, this is charge pump base, therefore delta phi will be 0. Therefore, this means that 2 delta phi essentially is 2 pi. So 2 delta phi is equal to 2 pi. So this means that now I have generated well-controlled pi phase shift. So here I am getting, of course, for one it may looks okay, so then I can get it very well by one inverter. But the point is that if we need more numbers, suppose 4, I put 4 of these phase shifters. So 4 phase shifters, then I will get 4 delta phi equal to 2 pi. Now delta phi will be pi upon 2. Then I can get something like this example. So according to the number of phases I need, I can put these phase shifters. And what are these phase shifters? If you consider the input signal is a digital clock, right? Therefore, effectively, I want to generate a phase shift. What does it mean? It means that I want just to generate a delay. Therefore, this is nothing else other than a voltage control delay element. So this will be a voltage control delay element. Because making a phase shift in digital domain is just simply making a delay. However, if delay of these components are not matched, therefore I may not get exactly pi upon 2 every day. Because then now this delta phi will be delta phi 1, and this for this will be delta phi 2, or this will be delta phi 1, delta phi 2. So I will get some error. So there are ways how to compensate it. So now this is one of the applications of, in fact, PLL, but because it logs in a particular delay, in fact it logs at what delay? Delay essentially is 0. Delay between these two phases are 0. So it logs at 0 delay between these two inputs, and therefore it logs at a well-defined delay between input and output of each one of these delay components. Therefore, that's why it is called DLL. So this is a very simple concept, and again, similar to the previous case we had, we can have a small signal model of this and then write the transfer function, everything. See, the reason is because the total phase change across the loop will be 0. Instead of 0, I wrote 2 pi. Because if this is a type 1, at least type 1 system, then difference between these two phases at the lucky condition will be 0. No, in type 1 also it can generate zero error in phase, not frequency. Right? Just double check.
Type 1, that phase difference is constant.
Okay, in type 1 phase difference is constant. Fine. So this should be at least type 2. Frequency difference is 0. Yeah. Fine. So it should be at least type 2. That is the point. Suppose if it is 4 pi, right? Then instead of here, for example, 4 pi, then it will be pi. That is one of the problems. Exactly. PLL has inherent, DLL ambiguity. Means that it can lock in multiples of 2 pi also. But again, there are circuits which can control this phase shift. But inherently, yes, it's possible. Okay, so now to make it, then just you replace this circuit with the same circuit that we have. That finite state machine, 3-state detector, phase detector, plus phase frequency detector, plus charge pump and loop filter. So the remaining part will be same. So now here you can use those current start inverters, for example, as VCD. They can be used in a ring oscillator to make a VCO. Okay. So therefore, we can have same model and then write equations. Okay. So suppose now if you look at the low frequency model of DLL, sorry, not low frequency, small signal. So a small signal model of DLL will be similar to PLL. So I have I show it by. So first one is large signal, second one is small signal. Here we will have voltage control delay element. So this is the control voltage. And this is the input signal. Control voltage is taken from output of phase frequency detector, charge pump, loop filter. Okay, all together. That will give the VCT. So now everything is a small signal. And this is a small signal. We will get an output phase. Which is equal to the input phase, and then I will have intermediate outputs out of this. So this will be essentially a cascade of stages. According to the number of stages I need, I will get different phases here. For example, y1, yn minus 1, and so on. So here, for example, if you look at V out as an output, that is enough, because if you have this, then each one of them can have a easily a simple relation with V out. Okay, one question. What is this? For VCO, we knew that, okay, frequencies, difference, change in frequency is proportional to the change in input voltage. So what is this word delay element? Gain of inverter. Okay, let's see. It will be okay. This. So what does it do? Okay, just suppose we have one single stage of delay. Okay, so this is voltage control delay element. My input is in fact small signal. Okay, so therefore I put large signal delta phi in, delta phi out. Okay, now answers. This is the question, right? Okay, what did you say? Delta phi? So suppose this creates a phase shift of delta phi, right? Therefore delta phi out will be delta phi in. Okay, one by one. Yeah, one by one. One with respect to phi, one with respect to VCT. Okay. So delta phi upon delta. So now what is this? So first one says that if I change input phase by some amount, output also will change by the same amount, right? First of all, shall I put delta phi here? I should not put it. It's not. So therefore this is 1. Okay, now it's VCT. Hmm? 1 upon. Okay, so what is that KPD? Okay. See, this is just 1. Okay. So it is essentially a delay element, right? So what does it do? It generates a delay. What is that delay? We call it TD. So this time delay is a linear function of voltage. Okay, assuming this is a linear function. Actually, it's not a linear function. If you remember, always it's not a linear function. If you remember for current stark inverter, delay was not a linear function. Frequency was a linear function. Therefore, first of all, it's not always a linear function. So this is a function of VCT. Okay, these are all large signal. So large signal is not. Therefore, small signal. So delta TD is equal to this F5 at some particular VCTL reference, right? So therefore, now if I write small signal, therefore I show it by small values. Td is equal to this f prime, which is a constant, which is actually that k PCBE into VCT. So for a small signal, I can write the linear relationship, but large signal necessarily is not linear. So this is time delay. Now just I need to convert it to phase. So how I convert time delay to phase? Multiply by 2. No. See, I have to have an idea of the frequency, right? So let's put it in this. So for example, I have this delta t is equivalent to delta t upon my cycle, right, into 2 pi. This will be equivalent to a delta, right? No, this is large signal. Just I wrote in the form of large signal. Essentially, it's a small signal. Phi in, phi out. I wrote in small delta because to know that we are talking about change in the phase, not absolute value of phase. So these are the small signals. So this is the way I convert it to a phase. So just I will have the relation. So time delay is equal to k VCDE into VCTL. All are small signal components, and corresponding small signal phi will be Td upon T into 2 pi. This is time. Therefore, phi upon VCTL I just replace, so it will be 2 pi upon T into K VCD. And what is KVCDE? That is important. See, this is the slope of variation of time delay with respect to control voltage in large signal domain. Because necessarily this is not linear. There are linear delay elements also. Okay, so therefore, and here of course when we are talking about small signal phi out upon small signal phi in, this is what? Because if phase changes by some value, the output phase also will change by the same value because their difference is a constant. Okay, so now in this small signal model, just this KVCD actually is this value. So we need just to understand how it comes, and then this will be relation between this output phase and input control voltage. So now you can derive it. I don't derive it. Shall I derive? It take time. But anyway, so now this is input phase, this is output phase, and this is a negative feedback, and then now we have the transfer function of this. So this is just a reference frequency, therefore it doesn't play any role in calculations. So in fact loop is like that, and this is the input phase. Okay, so with respect to phase it is quite clear. So therefore here I consider this has a total transfer function of H. Okay, HS. The entire pulse frequency detector, charge pump, and loop filter, HS. So this also we know, and then just leave it. So this is a small signal, the out S is equal to K VCDE multiplied by 2 pi upon T into VCTL. And what is VCTL? VCTL is actually is HS, right, into difference between these two phases, which is V in S minus V out S. So in some books, maybe KVCD and 2 pi upon T are merged into one, and they show it by the one coefficient. But in this way, you will understand it better. So this is a negative feedback loop. Therefore, V out S upon V in S will be same as before. Therefore, we have, depending on the order of H, we will get a second order or first order, and so on. Okay, so this will be CDE 2 pi upon T into HS Therefore, if you look, effectively, it is similar to PLL, because suppose if you replace it by charge pump transfer function, you will get similar relation. No, this is closed loop. Oh, no. See, look at it as a reference, right? That's fine. So this is some signal which is going inside. But we are not talking about this signal. We are talking just as a phi, right? And the output, it is like that. See, you have the signal here. Look at this. This is a delay element. It is generating phase shift. What we are interested is, this is our reference. So we are looking at this phi out. Actually, this is in fact phi out minus phi in. However, it doesn't change anything, because here you have a fixed phase, fixed frequency, which is given to this delay element. What we are interested in is how much phase shift does it generate because of VCTL. When we are talking about phase shift, then what matters what is phi in? Because this phi out actually is not phi out, it's actually phi out minus phi in, amount of phase shift. So that is enough for us. So this doesn't play any role in the calculation of transfer function. You look at it this way. Suppose there is one imaginary component which just mirrors this phi into this. I mean, even it's just simple. See, why doesn't have any impact? Because this is your delay element. In large signal, we are interested to see if I apply a change in input control voltage, how much phase at the output of this will change. What should be the corresponding delta P? But this delta P is not a function of that input. Therefore, it doesn't appear. When you make a transfer function, after all, this phi out is a function of this phase, because this is changing the phase at the output. It's a function of this. So it doesn't come here. It is like that you have biased it on some frequency, on some phase, and now you are looking at the change in the phase. Therefore, that bias point doesn't come in the transfer function. Okay, so therefore this transfer function effectively will be transfer function of output of loop filter to the input phase. So this transfer function, you double check it. Okay, now considering a complete phase charge bomb with the second order loop filter, so here we will get VCTL. So therefore HS will be pi upon 2 pi. You can derive it, it's very easy. R C1s plus 1. It will be order 1, type 1. So. You can derive it for yourself, double check it. And I is the current source of charge pump. Value of current source in charge pump. So again, as you see, at s equal to 0, this HS is not stable. And therefore, total transfer function of the loop will be write a final value y upon 2 pi k BCDE into 2 pi upon t RC1s plus 1, that is 0, and then we will have R C1 C2 this is square plus C1 plus C2 plus 2 pi upon t 2i upon 2 pi RC1 into S. 2 pi will get cancelled, 2 pi will get cancelled. There is one more term in denominator, I write it here. I K V C D E upon 2 pi into 2 pi upon T. See, RC and S will get cancelled. This is CS. Therefore, this is also CS. Dimensions match. If you put R, dimensions don't match. So it can't have R. There is an interesting point here. If you remember in PLL we use R to stabilize the system, right? But here actually suppose if I keep R 0, then system is stable. Just you put R 0 here. Right? We remove R. It's stable. What is the reason? There is a reason. Can you guess? We did all these things putting R just to stabilize it, but actually now in DLL it is not required. What is the difference with PLL? We should have phase shift in the feedback of what? Here we have phase shift in the feedback. In PLL also finally we have phase in the feedback. Phase shift. There is something related. In PLL we have VCO. Here we have phase shifter. We don't have VCO. So output of component is phase already. We don't need to integrate it to generate phase. In PLL we had to integrate. Therefore we had a type 2 system. And because of type 2 system it was unstable. Therefore here you can remove R actually. Therefore you just put 1 C. This is one more point. Okay. So therefore system here is type 1. R effectively is not required. Because phase shifter, or in other words that we see voltage control delay element has phase as output. So it's already stable. So what is the use of this transfer function? Therefore, this transfer function says that if there is some perturbation, some change in the phase of input, how again this DLL loop will settle. Because here everything is constant. We are not changing frequency. We are not changing any phase at the input effectively. But this says that if there is a perturbation in the phase of input, how it will settle. So it is only the effective use of this transfer function. It's not like PLL, because PLL we had different input frequencies, or if we had a divider, we can change the divider ratio to generate different frequencies, and therefore always this loop will go into a transient condition, and then it will come back to the steady state. But in PLL, usually DLL, we don't have such conditions. Change at the phase, right? So see, what happens is when you say it will change, when you have change in the phase, okay. See, if you look at loop, suppose input phase changes, okay, and then we have already some phase coming from VCD. So then now we will have a difference between phases. So the same transient which happens in PLL now happens here. So then now this loop filter, this charge pump will inject some current into loop filter depending on the change in the phase, whether it is positive or negative, and again it will stabilize the phase. Now here if we have a change in the phase at the end, because we want to have to design the system to be of type 2 at least, right? So if it is, suppose if it is type 2 and therefore this phase difference is 0, so what happens is that this VCTL will have some temporarily change, and then it will come back to its original value. So it's like it will go like this, or it will go like this. So it will be constant. However, interesting point is if I have a type 1 system, then what will be the final value of phi out with respect to phi in? Means that amount of error I will get phi out minus phi in. So at a steady state, suppose I put just S0, right? I will get a finite phase. Because it's not a type 2, it's type 1. Therefore, if you look at this DLL generates an error in a steady state between input phase and output phase. Therefore, it's not 2 pi. So we need to have enough loop gain. Otherwise, this error itself changes with process parameters and other issues. Therefore, loop gain of DLL, if you want to keep it as a type 1 system, that loop gain should be very large, so that this assumption of almost zero phase shift between input and output is correct. And the loop gain, of course, depends on the KVCDE and charge pump. So therefore, if I get the out S upon phi in S at low S, then this will be almost IK VCDE upon T IK VCDE upon T. Sorry, multiply. So this is 1. So output phase will follow input phase. Now, but what will be the amount of error? No, but here there is a conflict. It's very interesting. If out can follow phi in, these are small signal values, then the steady state error should be 0. Yeah? No, I'm just looking at what will be the DC value, yeah. If I have say a step change at the input, step change at the output will be some change at the output, finally these two will be equal. That is, of course, is expected, but what will be the error then? Then if error is 0, this is a type 1 system. What is error? See, actually, this type 1 understanding and type 2, all those tables and values are valid for PLL. For DLL, we have to generate new table. Oh no, yeah, I understand what you say. Wait, let us see. Phi out is, if phi in S is equal to, say phi 0 upon S, right? Therefore, phi out is essentially it is like A 1 plus S upon Z. S square plus omega n square multiplied by phi 0 upon S. Okay? I think you need to again increase the distance. So you can see there. Okay, so now phi out. What was the ratio? Ratio is 1, right? So this ratio A upon omega n square is 1. So this will be phi 0. Yeah, this is same thing. Same. It will follow input. See, because if you multiply it by S, you will get same transfer function by putting S equal to 0. I did same thing. Putting S here, 0. The same thing. Okay, so therefore error is not, error actually is 0. One thing else also we can prove the 0. Sorry, this you derive P in minus P out. And show this is P error. So therefore, if it is valid, therefore this means that here in type 1, steady state phase error is 0. You know actually what happens? Type 1 DLL is like type 1 PLL. Type 1 DLL for phase is like type 1 PLL for frequency. That's why these two give same results. If you have type 1 DLL with phase as the output and type 1 PLL with frequency as output, these two will have similar transfer functions. And frequency error is 0 in type 1 PLL. Therefore, phase error is 0 in type 1 DLL. Interesting. Okay, now there is one interesting paper. I will give you the paper link. Have a look. Because as I said, one of the problems is mismatch between delay elements, right? Other things are okay. Of course, one is this concept of ambiguity. It may look at 4 pi instead of 2 pi. That can be handled. We will talk. But look at this paper. This paper actually tries to compensate for process variations and mismatch. So, 0.722 gigahertz, self-calibrated, multi-phase DLL. So it is from Chang et al. IEEE JSSCC May 2006. So I would like to elaborate on this because this is one of the practical ways of overcoming this mismatch, and that is an important thing in DLL. Okay, so now we have a little time. Just I show you one more document from Motorola that is also interesting. I will give you anyway reference on model. Okay. So this is an application not for Motorola ICs. This is a discrete design. But that is interesting to look at. Okay, so again, this is design fundamentals, the same things that we have discussed, errors, type, order, everything. Then stability, root locus. Now here is showing even overshoot, amount of overshoot. Interestingly, now it has a design example here. And then bandwidth. Okay. Now in the design example, this is a design example. Consider we want to generate frequencies from 2 megahertz to 3 megahertz. Okay. And then with frequency steps of 100 kilohertz. We want to have phase coherent frequency output. Do you know what is phase coherent? Phase coherent means that we want to have zero error in the phase. So that the output phase and input phase are coherent. Means that they are exactly matched in phase. And then lockup time between channels 1 millisecond. Means that if you change the frequency division ratio, then it should take maximum 1 millisecond so that again it will settle to new frequency. So this is frequency range, and then now this is overshoot. Overshoot means that how much this control voltage of VCU will have overshoot. Means that what is the maximum frequency which is generated during transient because there is a oscillation in the frequency. So what is the maximum frequency? So you read this, that is, again, it's similar, the same way that we have, like here we need to have a counter, and then what is minimum value, maximum value, and then we will have an input frequency. So input frequency is constant, 100 kilohertz, therefore this steps of change of frequency is controlled by this counter. And then again, similar, of course, here instead of having a real VCO, they have ICs, IC have its own characteristic, for example, voltage versus frequency. Therefore, they choose these plots to choose values. So you look at this. One thing I wanted to tell you, like they have used an active filter, okay, instead of charge bomb. This active filter actually does the same work that charge bomb does, and by adding this RC and as a loop, as a feed-forward path, actually they are generating a zero. So transfer function of this will be similar to transfer function of a simple loop filter, first order loop filter that we have RC at the output of charge bomb. Okay, so it's similar to that. It has a zero, and if gain is very high, it has a pole at S equal to 0. Because when gain is very high, means A is very high, at low frequencies this path is open, and whatever signal you have will get multiplied by A will come to the output. If A is large, then means that almost at zero frequency, you will have a very large gain, means you will have a pole. Therefore, effectively, it's not S0, it's R1CS plus something, but that is negligible. So, therefore, it is effectively same transfer function that we implement using charge pump by putting an RC. Then look at this example. That is a very interesting and practical example. And according to overshoot, again the same thing. I mean, after all, here overshoot is important. We are usually look at the settling time of the loop. Then from overshoot and these plots of second order system. For example, they choose zeta equal to, I think, this is 0.8, this is 0.9. They choose, I think, zeta equal to 0.9. So that to have the very small overshoot. Or maybe this, I'm not sure. Just let me check. Which zeta they have? Zeta equal to 0.8 will produce a peak overshoot less than 20% and will settle within 5% at omega nt equal to 4.5. Therefore, lockup time is 1 millisecond, and we want to have 1 millisecond lockup time. Therefore, omega nt will be therefore T will be 1 millisecond. Therefore, omega n will be derived here. Therefore, according to overshoot, deriving zeta, according to settling time, deriving omega n, and therefore choosing values. That's a very interesting example because it is based on discrete ICs and they choose components in such a way they are close to the available discrete components, and this is the loop. It's a very nice example with all values, and this is the final design. This is that amplifier, this is on chip, okay, with the gain of A. This is that RC, series RC, this is off chip, with these two R values at the output of this phase detector. And this bipolar transistor is just the buffer, with the input of buffer and this resistor, output of this phase detector IC. And these are counters, and this is VCO. It's a very nice example, and then they have shown practical values they have achieved. They have designed for n equal to 30, maximum division ratio, therefore, which is zeta almost equal to 0.8, and then therefore they get higher value of zeta for less value of n. So when you want to design, you use the maximum value of n because that will give you the maximum loop gain. That will give you the minimum value of zeta. And then when you reduce n, you will get less loop gain, therefore your zeta will increase and it will be stable. Therefore, design always will be based on n max, maximum divider ratio. And then they have even experimental results, and then they show that, for example, how this control voltage changes. As you see, exactly you observe this overshoot and then settling. This is the locking time. So it's a very nice example. I will put the link to this example. Okay, so next time we will, so this also, will be useful for the design. Oh, by the way, about assignment. See, are you, finally, how many groups will be groups of 2? Is there any odd number? Did you check? I asked you to check. So anyway, I asked you to make make groups, and then tell me whether there is anybody left, if the number is odd. Okay, so then see, you make similar thing. Now you use current stark inverter as a component for ring oscillator. Therefore, you can make a simple digital VCO. Now the specifications will be this. this will be, I think 5, right? So one of you can focus on pulse frequency detector, one can be. So what we want to have is similar to, look at this design example in Motorola, similar thing, but you consider we have the reference frequency equal to 200 kilohertz, and channel spacing will be same as this, and then frequency range (800 megahertz to 900 megahertz). And settling time almost 10 microsecond, around 10 microsecond. Oh, sorry, this is not reference, sorry, this is channel spacing. You can call it channel spacing, you can call it frequency spacing, it depends on the application. Okay, so right now we are not looking at this particular application, but suppose you want to have a synthesizer with this different range of frequencies, and F in, which is impact reference, will be 20 megahertz. Okay, now we want a range of 800 to 900. Okay, so it's around 100 megahertz. So now to make it different among different groups, so we will change it. So we will keep reference frequency constant, we will keep channel spacing same, but then we will change range of frequencies. Okay. And one more thing is that divider. Right now, I didn't get time to talk about this prescaler and then how to make the ratio. So right now, what you do is you can use just simple counter. Okay, therefore, if the divider ratio doesn't come correctly, you can adjust this frequency a little. Okay, so this frequency is controlled by the counter. Now to make it different, you should not use same counter. What I'm saying is that you should have a design different VCOs. Means that the range output center frequency of VCO should not be same among all groups. Therefore, you can use same charge pump that's you design, but I don't recommend even to do that because then you don't learn. So, but don't have same frequency for your VCO, and then don't use same values of delay for your current start. So what I mean is that characteristic of delay element for that current stop inverter and therefore your ring oscillator should be different. Suppose all of you may use same number of stages for ring oscillator. Therefore, to make the frequency different means that your current stop inverter should be different. For example, you can use different size of components to get, or you use different reference current, right? Use different reference currents. This is one way of doing that, because after all you have just one inverter and delay is controlled by the current. Therefore, the best way is to use different levels of current. Okay, therefore none of you should have same VCO after all. So groups of two. And if, see, I leave it to you, it's better to simulate everything using cadence or mentor tools. However, if you see it takes time, because we want to see how we can generate this 800 to 900 megahertz, then you can model it as a Simulink model and then simulate it by Simulink. Because when you design the loop filter, then you know what is your zeta, what is your omega n, what is characteristic of your VCO. Therefore, everything can be modeled in Simulink. Okay. No, just like a block diagram, and for example, for loop filter, you put a transfer function. Minimum size, nothing is specific. Yeah. And even for current source, it's up to you, because after all, what we want to achieve is to generate this frequency range. You have a counter, and settling time should be 10 microseconds. Therefore, there is enough freedom. There is no limitation even on the current I of the charge pump, because here there is no limitation on the power. Of course, don't make it like several ampere. That is too big, but it's okay. It's not limited in the current. Channel spacing, for example, you have 800 megahertz. The next frequency you want to generate will be 8.2 megahertz. Next will be 8.4 megahertz, right? The input frequency is 20 megahertz. Yeah. So see, for example, input frequency is 20, and then you have a divider. Yeah, steps will be steps of this frequency. What we can do? No, there is one way. See, if it is integer, that's why I didn't talk about prescaler. If it is integer, yes, means that you will have divided by n is integer. But if you have a rational number, say for example m upon n, then it is possible. So one thing we can do to make it easier, you make it input frequency to be, you make channel spacing to be 20 megahertz. That is easier. Then your counter also will be smaller. You make channel spacing 20 megahertz, no problem. Because this is essentially for, say for example, some digital applications. Usually, see, for, say for example, wireless transceivers, they're actually, this spacing is very small because their channels are very close. They don't want to waste bandwidth. But here it's fine. It is just a matter of learning, so it's okay. So you use a conventional divider with 20 megahertz spacing. So therefore, don't use same VCO. So delay element should be different. And also don't use same charge pump. Even your charge pump also, suppose if one group designs with a current of say 50 microamp, you don't use again 50 microamp. So I will ask TS to check this point. So don't use same current values for charge pump. So in this way there will be different designs. Okay, effectively counter is straightforward. Effectively you will design one charge pump, one